Hey guys, we're gonna get started. So if you remember on Thursday, we went over the code for the CIFAR challenge, right? And we completed everything from getting the images from a folder and loading them in until we created a tensor base, right? And that's a nice unit to have of the data. Now we're going to proceed to complete the rest of this, which is to convert the data into data loaders. And then we're going to define the neural network architecture, the very basic neural network architecture, performance, etc. So hopefully I'll be able to complete that code today. And then you'll have basically the working code with performance metrics for the CIFAR-10 challenge. Remember, of course, you need to improve upon that in order to win the challenge, right? Okay, so we're going to continue using the Scholar, GPU Scholar. So I'm going to go and copy the link here. I want to just continue with the same script I had before. So that should still be in memory. So everything should still be there. And I'm just going to go to Jupyter Notebook. Okay. And then here I'm going to select a GPU. Give it a minute. This one stays there for debugging purposes, as it says. All right, so it's initializing. Yeah, all right, here we go. So I'm going to initialize the the instance. So I should have everything now. I'm going to click on desktop. And the Jupyter we were working on, the data is there. And then we were doing, I think it was this one, right? In class, no, that's not. In class CIFAR-10, probably this one, 5 days challenge. Yeah, there we go. All right, so I'm going to just rerun this script just to make sure everything is working. And then after that, we're going to pick up where I left off. Are there any questions before I begin? Yeah.
Is this on GitHub?
This script, is it on GitHub? Not in this form. So what I'll do is when I finish it, I will upload it. Hopefully by the end of today, yeah. I don't think I've uploaded this, because it wasn't complete. Yeah. All right, but I do plan to post it. All right, I will use actually the iris code that we saw already to extend this one. Okay, so it should be pretty consistent. So if you've already gone through the iris and you know how it works, then this is similar. Okay. So, but basically my objective for today is just to get this, to get a performance metric that's, an F1 score on the test set. And that should say basically, the minimum that the competition, the minimum value for the competition. And then from there, you guys can go up. Okay. All right. So what you do here is, if you remember, so I have data loaded already. So I'm just going to go to the kernel. And I'm going to hit restart and clear output. And I'm going to refresh everything so I can rerun it again. Okay. So then I'm going to save. So everything is gone now. So, of course, we load the libraries. Let's give that a minute. We're using Torch Vision. Okay, it takes a little bit. Okay, then I'm going to hit Torch CUDA is available, true. Devices, we have one. The device is ID 0, and it is an NVIDIA A30 this time. Okay, our data sets have already been uploaded to the GPU Scholar. We remember you have to use this data set and you have train and test. You need to train your model on the train set, and then the competition is going to be based on your result on the test. All right, so let's go ahead and hit run here. So I'm going to do train. This is the function for reading that we went over. Okay, so I think actually we just did the train, huh? Yeah, we just did train. So now today we have to repeat this for the test set. Okay, so that's what I'm going to do. All right, so data set train, labels train, targets train. It'll be very repetitive. I mean, I could do an object-oriented thing, or this code could be better. How about that? But I'm just gonna repeat it kind of as is, and I'll let you guys improve upon it. So we have for the train set these two lists, and then basically this for loop, right? So for folder in raw data train. So that's that path for train. We basically iterate through all the images, okay? And we are adding the labels, okay? So all this I explained last Thursday, so that's why I'm going a little bit fast. Here we add the ID that we're going to use for the training. This is how we read the image, which remember is RGB. And then we have, we read the image with image IO, then from NumPy convert it into a torch tensor, normalize it, and append it to the list, basically. Okay, so all of this was discussed before. So really our test code should be very similar, except I'm going to change the list names. All right, so that, can't remember if this took a long time. Let's do that. You guys remember how long this took? It's about 60,000, 50,000 images, 50,000. So it's reading each one. Okay, finished, great. All right, so let's count. This is important. So there's 10 classes, 50,000 images. The shape is 3 by 32 by 32, so that's one image. Okay, and then I took data set train. I created a torch stack called a data train. Okay, changed the data type to type long. Okay, and then I showed you, yeah, I showed you guys how to save it basically. All right, so that's it's processing. Now, if we print data train, which is this one here, we can see that it has a shape of 50,000 by 3 by 32. Okay, we can take a look at the shape of targets train. Well, that's 50,000. We can look at the shape of just one individual item, and it's 3 by 32 by 32. You can also look at ranges, and you can see that we have the classes. Does that make sense? Okay. And then I think we did find the last thing we did is we just looked at one of the images. So I grabbed like image 46,000, got the data in there, convert it to a pill image. And then you can see this one is a photo or picture of a cat. All right, everyone with me? All right, the next thing we want to look, if we're going to be consistent with the iris data set, is we want to look at the balance of the classes. That's the next thing that I want to look at. So if you remember, we used the histogram for this. So we just have to make sure that we have the data in the right type. But I'm going to try to do plt.histogram. And I want to provide in here, it should be, oh, let me add. class balance. Okay, I just want to know if this is a balanced data set. This is really important because it would tell me how difficult a task it'll be, right? So we want to know that. Okay, so we can provide in here, let's see. So we got data train and targets train. So targets train should be it. This one. Targets train. And then the method was bins auto. Okay. And then plt.show. T is not defined. Okay. Okay, so we don't have map plot. So what would this be? Yeah, so import matplot matplotlib dot pyplot as pl. All right, so and again, really, really important to look at the balance. So let's try it again. Could be taking a while. Did it run for any of you a little bit faster? No. All right, so pyplot works better sometimes with NumPy. So I'm going to change this to NumPy. Do you guys want to follow along? Was that your thing, Aiden? But you can't follow along with the GPU though. Oh, you don't have the data. Yeah, exactly. You won't be able to follow. I will post. I will post this at the end of today for sure. Let me kill this because it's taking a long time. It might be that it was, but let me change it to NumPy. So there are 5,000 in there. I kill this again. All right, so 5,000. Also, import NumPy SAP. Right. All right, so those are the labels 0, 1, 2, 3, 4, 5, 6, 7, 9. I think this is just pretty slow. Oh, there it is. All right. So I think I was missing the NumPy thing. All right. So what can you guys tell me from looking at this histogram? What does that tell you? It tells you something very important about for machine learning purposes.
Balanced it.
It's a balanced data set. Okay, what that means is you have all the classes there from 0 to 9. And how many samples do you have? About how many per class? 5,000, right? And there's 10 classes, so we have 50,000. So good. This makes your life easier, right? So you can get good performance, hopefully, with a really good model with this one. It's less challenging. All right, so let's go. So we know that fact. Now, we want to proceed to do, we have the data, right? The images, and we have the labels. We don't have to do train test split here because we already split the data, right? We already have a train set and we have a test set in one folder and the other, okay? So instead, what we want to do is we want to create the data loaders. But before I do that, I want to load also the test set, okay? And the test set should be very similar. And I want to perform that task again. So I'm just going to copy the code. All right, so I'm going to say test data. Copy these. Okay, so this is going to be test data. So markdown run. All right, I'm going to change these to say test so there's no confusion. And we're going to reuse the code. So basically, you could have just written a function and have been more efficient. And I leave that for you guys to do. Okay, so then this is really what does all the work, really, right? So here. Okay, so run this. Now we need to inspect that for loop because there's going to be some differences, right? So the path is now going to be raw data test. Okay, so it's this one. It's going to be raw data test. Okay, so that's now from the other folder. That's really important. Okay, for image and OS list. That's fine. Raw data test. Notice you have to change this. Test. Folder is, yeah, it's right here. If folder not in labels test, right? Labels test. Append folder. Targets test. Append labels test. Index folder. Then image read OS path, raw data test, folder, image, pill image, right? Torch from NumPy, image R, float, and then finally dataset test append. Do you guys see that? Any questions about this? Pretty straightforward, right? So should work. Give it a second. There's only 10,000, I think, images here, but we're going to confirm that. It's really important.
That would be 1,000.
Hopefully. Yeah, hopefully. So this is actually, if you were ever doing something like this, before you commit to anything, look at this. Because really, machine learning with imbalanced data sets is way more difficult than balanced data sets. Okay. All right, so this ran. That's good. So now we're gonna do the inspections here. So basically we can print length of labels trained, targets, one image, and then we want to do this part here. Check, yeah, really. So I'm just gonna copy this part. Okay. So add that in there. So this is data set test. Okay. Torch stack. This will create data test. It's really important. This is targets test. This is going to be targets test. Torch save data test. Targets test. And labels test, right? So the test set. Okay, and you want to call this CIFAR-10. I guess I should have called this train. So this one, it'll be tested. Okay. All right, so basically now let's go ahead and run this one. Okay, done. All right, so now we can print data test.shape. Okay, there are 10,000 in there. They're 3 by 32 by 32. These are your images that your model needs to classify these and do better than everyone else. Then we're going to also do targets test shape. So dot shape run. All right, so there's 10,000. Okay, so what else do we need? That gives us a lot of information. So now let's just do the histogram. So I'm really just going to copy this one. Copy. All right, I need to use targets test here. NumPy, bins, PLT show. Okay, and what do you think? So there's also the 10 classes, 1,000 each for 10,000. Do you guys see that? And there you go. This is basically the challenge. So these are like the parameters of the challenge. Okay, now we have everything in train and test, and now we need to proceed to create our data loaders, and then we're going to start defining our network architecture. Any questions?
Question.
Yeah, please.
Would it be better to like shave off data if you're working with an imbalanced data set? Just
Like
remove-
drop the dominant classes.
Mhm.
That's called I think undersampling. Yeah, there's a technique. One is called undersampling, the other is oversampling. So you can drop some to like balance it or add synthetic data. That's also a possibility. Like you learn what's the mean and the standard deviation of the data, and then from there generate new samples with a little bit of noise. So I can't really tell you which one will work better. It's
but not imbalanced.
Hmm?
Not imbalanced.
No, at the end of it, you just have to look at here. I don't have to worry about balance techniques. So I just do this. If I had a highly imbalanced data set, then I'm going to try this first, the normal approach, then try oversampling, undersampling, but it's a much more difficult challenge. So it takes a lot of work. And it depends on your ultimate outcome also. Yeah. All right, any other questions? All right, so the next thing, as I said, most likely the data loaders. So we've done this before already, and most of the time you want to use a data loader for your data. That just makes your life easier. Okay, so once again, we just have to worry about the conversion of data types, right? So here we're going to have X train, X test, Y train, Y test, right? So we might want to think about that. Oh. The data is already tensors, right? So basically, the data loader likes to take, we do have actually this, likes to take a list of tuples. But I was just thinking of how to make this into the conventional, the naming convention. So what I'm gonna do is, this is test data. So I'm gonna grab the train data, which is in these two. And I'm just gonna change the name. Okay, so this is just so that it's more familiar. So in here, I'm gonna take these two. So what is this one? Data train should be what? X train, correct? Do you agree? And then targets train should be what? Y train. Why do I do this instead of using those names? Because X train, Y train means a lot of things to me. I know what I'm looking at when I see those names. Whereas if I leave it as data train, targets train, just more confusing, right? So my brain will get more tired, so I'm trying to make things simple. All right, so this, I want to do this. And then I'm going to repeat that for these two. So it's just data. I'm just going to copy. All right, so then, code that you have somewhere else is, you'll be able to reuse it more easily. So now this one should be X test. And this should be Y test. Right? Everyone with me? So it's just a little bit simpler to use the naming conventions. Okay, so now we have those. And so we have to think about how to create. Now, these are torch tensors already. So to create the data loader, if you remember, let's go over here. The data loader wants, let's say, train underscore DL, right? And the way that we would initialize it is to say torch dot utils dot torch utils dot data dot data loader. Uppercase L, data loader. And it takes basically a list of tuples with X and Y. If you remember, we did this with the iris data set, so that's what I'm going to repeat here. So I'm going to call that, I'm going to call it CIFAR train list, but it's something I have to create first. Then we need to specify the batch size. Remember that when we're doing training, we are going to grab data in batches. So batch size is going to be equal, let's say, batch size parameter. I'm just going to use 16. This is important at this point because of your GPU. You're going to be grabbing big things, right? And if that's too big, that batch size, you're going to run out of memory. All right, so be aware of that because it's a bigger matrix multiplication. If you did batch size of 1,000, that's all of those rows, and then so you might run out of memory. So definitely want to control it here. So just keep it as 16 for now. So batch size like that, and then we want to say that we want to shuffle, right? So shuffle equal true. Remember that the data gets randomized every epoch. Every epoch, basically. Any questions? All right, so then we know, I started there because I know that what I need is CIFAR train list. I need that thing to be created. So I'm going to go over here. Oh. Copy. All right, so I need to create this list. And this list we already know is just a tuple, basically, or a list of tuples where you have the image and the label. then another tuple, image, and label, and so on. And if it's in that format, the data loader can read it in quite easily. All right, so let's go ahead and do that. So how do I do that? I'm going to create a list comprehension. And this is similar code to the iris one. So for I in range. Okay, and I need to specify, I'm going to iterate by index, maybe. That's my first instinct to do something like that. So I want to know, should be 50,000. I could also hard code it, but I don't recommend that you hard code anything. So let's take a look at xtrain dot shape 0. This should be 50,000, correct? And it is. All right, so that's the variable that you should plug in here. So I'm just gonna do xtrain dot shape 0. Okay, so now we have that. We're gonna grab the indices I, and we're gonna basically plug in here tuples. A tuple, remember, is just a list of two things. Okay, so in this case here, we're gonna put in the image img, and here we're gonna put in the label. But these have to be all, torch tensors already. Okay, so that's the other requirement of this. Does that make sense? Yeah. But we already have them as torch tensors. Now, keep in mind, one thing that we have currently is that the images are 32 by 32 by 3. So we need to deal with the fact that all that you know how to do right now is to flatten things into vectors, correct? And you process things like that. So there are other tricks, but I'm only going with that one for now. All right. So let's think then, okay, where do we have? So we have the labels. See, that's why this is nice. Since I changed the name, now it's more, I remember what I need to do. So here I'm going to say, I'm going to do train. So then y train index I, and then this should possibly be item, right? So we can grab the actual value. So it wants the number and not like a scalar vector or something like that. So it just wants the number. But we'll test this. We'll try this out in a sec. Also, you could do this. So remember, that's the beauty of, Jupyter notebooks, etc. Just do that. And you know that, an index in there is like 7 or something, right?
Yeah.
Oh, do I? I'm sorry. Yeah. That one. All right, so I run this one. 0. Let's try another one. 0 also? Oh yeah, because, okay, so it needs to be like 20,000, right? 30,000. This will be definitely another. Yeah, there we go. So you guys see that? That's a lot of the time, data science is this, just what is that format, right? And that's what I'm trying to emphasize here. You can always create a data loader if you just put your data like this, and you can't. A list of tuples where one is a torch tensor and the other one is the actual label, and that'll work. All right, so now so we know this one will work. So now we need to deal with the image. So the image is coming from xtrain I. And if you notice, this one is the actual tensor. Got it? How do we confirm this one? Again, you can just copy it, paste it in there, just pick a value. It doesn't matter, 78. Get rid of the I. All right, that's a tensor. We know that's a tensor. So we're good. Any questions? All right, so now let's go ahead and run this one. We need to create this list. So run. Okay, it's processing because it's a large data set. Keep in mind, the images are not flattened currently. They are, in fact, 32 by 32 by 3. All right, it finished, not too bad. We can now then, in theory, convert it into a data loader without having to do anything else. Let's see if it breaks. Didn't break. So we are ready. Okay, great. So now we just have to repeat that same process for the test set, create the data loader for the test set. Let's just do that now. And then, believe it or not, we should be ready to run CIFAR-10, create our neural network, and measure performance. Any questions? Yeah. So hopefully, as I said, we'll finish this today. All right, so now let's data loader for test. Now let's do the same for train. Let's do the same for test. I can literally just copy this. Right. So let's change this to test. Change this one to test here. Change this one to test. And this should be test. Right? So, and then over here, we're going to do test DL. So test DL. Now, for the test set, we don't really need to create batches. And the reason is we're not going to be training on the test set. We're only evaluating. So it's just what is called inference as opposed to the training cycle. So it's less intensive on the GPU. It still requires power, but not as much. This is, for instance, in industry, NVIDIA makes the GPUs for training, and Intel, I think it is trying to position themselves as making the chips for inference. So not as powerful as the GPU ones, but optimized for that task. Okay, so that's kind of what we're going to try here. So test DL, we're going to change this to be test. Batch size, so we're going to change that to just, for now, I'm just going to set it at 10,000. You guys can play with this if you want, but I think memory-wise, this should be fine. Okay, if you have issues with memory, of course, decrease that. Does that make sense? But because there's no training of the weights, no, no calculation of derivatives, things like that, the GPU should do just fine, I think. All right, so yeah, so that's basically it. The shuffle wouldn't matter here because you're just going to give it 10,000. But every time it'll shuffle. All right, so then for this to work, we need to define test list. So this X test, Y test, X test. Yeah, so let's run it. Okay. And there you go. We are ready. So once you have the data loaders, you are really, ready to go. We can now, run data. So what we need to define now is the next steps, which are the neural network architecture. I will provide for you guys a multi-layer perceptron once again, and a deep learning algorithm of certain layers. We need to provide the training loop, call the core functions to do the training on the GPU, and measure performance, basically. That's it. Okay. So, and this is exactly what we had done before for the iris dataset. So if the iris dataset was a lot of information and it seemed hard, now this one starts to become easy. You see that? That's the beauty of this. First one is hard, but because you're following pretty much the exact same pipeline all the time and almost the template, it starts to become almost super easy. Got it? All right, so let's start defining the architecture first. So I'll just start with the simplest one, which is probably the multi-layer perceptron. Okay, we have to make some decisions as to how we're going to do this. So I'm going to call this architectures. Am I recording? Yeah, I am. Yeah. All right, so architectures. All right. Let's go ahead and define the multi-layer perceptron. So you guys should know how to do this, right? It's a class, correct? Class. So we can call this MLP net. Do you guys remember what goes here? Not so. And then dot module. Can you tell me why? Like, what that is? Yeah, it's class inheritance, right? So it's just you learned that concept, I'm sure, in one of your OP classes, and you're like, I will never use this. Why am I learning? I will never need this. There it is. You do need it. It makes your life easier, right? So we are inheriting the NN module from Torch, and that just makes our class super easy to define. Okay, so I'm gonna go now and do this. Okay, so remember, this has two functions, basically, the constructor and then the forward function, but we can add more. You know, like generative models, for instance, like the GPTs or those that generate images have a generate function, you know, and things like that. So there's other functions you can add in. I mean, you can, it's your class, so really you can do whatever you want. All right, so let's do init the class. Okay, and we're going to define, so this is pretty standard, 2 underscores, init, 2 underscores, and then self, which remember self is the reference to this object when it gets instantiated. So then we do something like that. Okay, and now we initialize the inherited class, so we can say super dot underscore underscore init underscore underscore parentheses. Okay, and there you go. After that, pretty much, you know, we can start defining things. So in the previous example that I gave you, I believe, for the iris data set, we only did, yeah. So I'm going to stay consistent to that. So we did the linear function, which I've explained several times, that that's the w equal, no, sorry, the y equal wx plus b, if you remember, right? So I'm going to use that linear one. And then I always use these thing called activations, which it's one of the next, you know, like once we're finished with this, I can start getting into all the theory of this, and we're going to look at why activations are so important, etc., what they do. But basically, these are the main building blocks of the neural net. Okay, so I'm just giving you this so you can start playing with your assignment. All right, so then we need to initialize these variables. So self dot linear one, that's going to take nn dot linear, which is the actual PyTorch function. And if you remember, we need to define here the parameters. So I'll come back to this because this is where the architecture of this comes in. We start with the MLP because the MLP is simple to set up in a sense. Then here I'm going to say self dot activation 1. And I'm going to invoke sigmoid. But there are many other functions that you can try out and play with. Okay. Then I'm going to need for the multi-layer perceptron another linear function. So linear 2 nn dot linear, and this also needs a definition of the dimensions, and finally self dot activation 2 nn softmax. If you look, this is the exact same definition of the iris. So that's, you know, you already know how to build these neural networks. A lot of it you're reusing. You just have to modify some aspects of it. And softmax, it's applied on dimension 1 usually. Okay, so specify. All right, then I'm going to just, I want to complete this and then we'll get into the shapes. So now we perform inference, which is prediction, right? So basically we need to take the data, run it through the neural network and predict something. Okay, so that's done in the forward function. So define forward. Forward takes self, but it also takes X, which is the input that is going to come into it. Whether it's a batch or an image, it'll work just fine. Okay, so now we do colon. And once again, I'm just reusing all that code. So now you should be able to do this. Like, all right, so self dot, oh, lowercase, linear one takes X, right? And it processes it. Then I'm gonna do X self dot activation one, which is that X that goes in. Then X will have self dot activation two X, right? No, sorry, linear two. 2X. And finally, this one I'm going to call Y pred. And it's going to be self dot what? Which one? Activation what? Oh, yeah, activation two, right? Yeah. Yep. Okay, so activation two, and it takes in the previous X. So it's like X goes here, comes out here, then this X goes here and comes out there, then this, and so on. And you can change those variable names if you want, but just, I like to just keep it consistent. And then finally, we return, forward should return Y pred. All right, so that is exactly what we had done before for Iris. The question is the architecture, right? So now let's think about this architecture. Are there any values? So obviously what I am talking about is the values that go here and the values that go here. Are there, and then this is a multi-layer perceptron. So it's got one input layer, one hidden layer, one output layer. So is there one value that we already know here? What is 10? Where does that go? We know it, you're right. In the end, yes, very good. So it would go here. If you remember with Iris, that number was 3. You guys remember that? All right. So then really, the other question is with Iris, what was this number? Well, you're right, but with Iris, what was the number? 4. The 4 features of Iris. With MNIST, which is 28 by 28, 784 if you flatten it, right? You guys only know how to process, use neural networks with flattened vectors currently. There are other approaches, like you could actually give it the image as is, but that's something else. So I'm not going to show you that initially, obviously. So instead, we need to, as you said, flatten the image. So how do we do that? Okay, so you want me to just...
No, like, not do that, but like the output, whatever the answer is, so where that number is.
I mean, that works. Right, so you're right, good. So that's 32 by 32 by 3, but you're making a decision that you're going to flatten the color images, correct? Yeah, all right, great, that's it. You've done the architecture, just don't forget that currently the images in the data loader are not flattened. They are 3-dimensional, so you're going to have to do that before you give it into the neural net, because the neural net is expecting this vector. That's a very large vector, by the way. Okay? All right. So what is that number, actually? So we can, print it if we'd like. So let's see, that number is 32 by 32 by 3. What is that? 3072. That's what that number is. So we give it an input vector of 3072. The output vector is of size 10. And we're building a multi-layer perceptron. So what's the value here? This value here determines the hidden layer, right? That's the number of neurons. If you remember, whatever you put here also needs to go there, right? From one layer to the next. So what number do you define here? Yeah, but what number? Like you decide. There's no science here, or there's only, you define it. And all of you can try different numbers to see if that's all that it takes to get the best model. So how many neurons? Why 200?
Then it becomes small.
Hmm.
It's good to go from 200 to 10.
So the funneling effect. So here, I think I mentioned this before, that in Iris and other data sets, we couldn't see the funneling effect. But when you're dealing with images in general, you always see this funnel. So it starts really big because its images are huge, and then you want to make it smaller. And actually significantly smaller, like 200. And that's almost like a good analogy, I would say. If I tell you guys that this is due in 2 months, you will start the week just before, like in 7 weeks, right? That's when you'll start. If I say that this is in 3 months, you will again wait 2.5 months to start. So basically by using 200, you're like constraining the resources of the neural network in a sense. Do you guys see that? So it's like an analogy that you're forcing the neural network to do more with less and be more efficient. Questions? All right. So we've defined the architecture. Do we need to do anything else for this architecture of a multi-layer perceptron? No, right? It's very similar to Iris, and now you know how to modify it a little bit. But that's it. So what I'm going to do now is we'll define. And then it's not the. Did I not do that either? Okay. Hold on. So let me go to the here. I probably don't have any of the PyTorch actually. So I usually like, for whatever reason, I always do those in a separate cell. So let me. So import, so Torch is there, Torch utils, Torch vision, train test split is there, but these are not in there. So import Torch dot nn as nn. We also need import Torch dot nn dot functional as f. And we also want import Torch dot optim as optim. Same things we used before. Like I said, remember a lot of like all the background is in these things, basically. We are also going to need sklearn metrics and all that, so I'll add those in a sec. But now we should be able to have the libraries to instantiate our class. So just run it. So it's loaded. It's on the GPU. The beauty of running this on the GPU is, hopefully it'll run some fast. If I was doing on the laptop, I would have to just pick like 2 or 3 classes out of the 10. I wouldn't be able to do all. So now hopefully this will work. And it does. Okay, so now that I have an architecture, just like before, I'm just gonna go ahead and do what? Define my train function, which is exactly the same function I used before. That's, again, the beauty of this, that once you define like a template set of code, you can reuse it a lot. And really the hard part is always dealing with the data. All right, so we're going to create the function, define training loop. And we need to provide the number of epochs that we're going to define. and epochs. We also want, I'm gonna, just to be consistent. Comma, model, comma, loss FN, comma, and opt. All right, these are the same parameters as before, not the colon. And then we're gonna say for epoch in range and epochs. Remember, the intuition here is that you're feeding all the data set again, multiple times to the neural network. That's just, you know, how it works. Okay, for epoch and range and epochs, then this is where the data loaders come in and do a lot for you and make your life easier. So you're going to say for XB, comma, YB in train underscore DL. I have looked at a lot of like books, blog posts, etc. This is always what people use, thankfully, as it makes things a lot easier to understand. But this is a very consistent approach. All right, so the 2 for loops are there. You can now grab your data. It's going to be batches of 16. Now, here comes something interesting. So this is the same as before. So you're going to say ypred, you're going to invoke the model, and you're going to give it xb, right? But you have one problem. What's the problem? The tensors in xb are still 32 by 16 by 3 by 32 by 32. And that's not going to work for you because you need to, your neural network is 3000 something, not 32 by 32 by 3. It's not a cube, it's a flattened vector. So this is where you conventionally do this, okay? Why do you conventionally do this? Because what if you change the architecture to a model that can take 32 by 32 by 3? Then all of the other code you wrote still works, and you just make the conversion here. Does that make sense? So that's why you kind of want to do it here. So what that means is here we need to reshape XB, right? So we need to reshape XB. So what I'm going to do here is I'm going to do this actually, and I just want to print the shape of XB. How about that? So I'm going to say print xb.shape input. This just holds the program, and I want to see what happens, okay? Let's, oh, I think it's, and then I need to invoke the core function. So I'm going to do train. I need also number of epochs. So how many epochs do you think we need? How many epochs? Well, it's a lot of data, so start with, Yeah, it's a lot of data, so start with something small just so that you make sure everything runs, and then we can start increasing it. Okay, let's just say 100 for now. Now I'm going to invoke this function. Okay, but to run it, we're going to need several things, right? So I also need the model instantiated. Yeah, so I need the whole, all the core functions need to be invoked. So there's no, you know, I kind of like to use this terminology, core functions, but there's no real need to do that. Okay, so the core functions are to instantiate the model, right? So model, that's exactly how we did before, MLP underscore net, right? And that's it, that's done. Then what else do you need? You need opt. Opt is going to be the same thing as before, torch.optim.atom. Okay, this is the optimization for the whole changing of the weights, etc. What goes in here? We need to tie the model's parameters into this. So I like this feature actually. So these are the weights, right? So model.parameters is like in the formula y equal wx plus b is the w and the b. And those values you can move around. Okay, here's an example. Let's say that Quentin, right? Quentin, you have a GPU and you spent a week training your model. And right, and then it's a pretty good model. And then Aiden doesn't really have time to train, but Aiden somehow is in the same team as Quentin. So what Quentin can do is, Aiden, here you go. I'm going to give you the model.parameters and you add them to your own model. And now Aiden will have a copy of Quentin's model. Do you see how that works? As long as he creates the same architecture. So they have to have the exact same architecture. And it fits. That's called transfer learning. It's really important in machine learning today. Any questions about that? Questions, right? Great. So this is an important concept, okay? Being able to do this is like extremely powerful. All right, and then the learning rate, we also need to define that. So it's going to be learning rate. The learning rate is actually really important. You almost never know what learning rate to use. Where was n epochs? That right. Let me add a cell here. I'm just gonna this one here. And I'm going to put learning rate in the same place. So learning, because these are parameters that you might need to change a lot, especially the learning rate. It's one you can play with. So I'm going to start with 0.001 for now. That could be 0.003, 0.005, could be 0.01, could be 0.3 zeros and a 1. You got to play with it. All right. And also, we'll talk about this a little bit later. So now that we have that, the next thing we need to instantiate is the same thing, something called a loss fn, this function, which is what's going to compare the predicted and the real. And it's, like the Euclidean distance, if you remember, we would take a value in another and calculate a distance. So this takes the predicted and the real and calculates a type of a distance. Similar idea. So loss fn, this one is easy to set up because PyTorch provides something. Now, in this example, we're going to use cross entropy again, which is what we used before. So there's basically just two of these. MSE when it's a regression problem, cross entropy when it's a classification problem. That's it. All right, so then you can do cross entropy, but there are several versions of cross entropies. And sometimes, using one over the other helps a little bit. All right, so I think we have everything now. So loss fn, opt, model, and n epochs, right? So we should be able to run this without errors. So let's go ahead and try it again. Notice I'm not running anything through the neural network. I'm just doing, okay. Right, where is, oh, here it is. Okay. Okay, there we go. So this is where I was getting, or I was trying to get to this, if you remember, right? So what are we seeing here? I used the train data loader and I grab XB and YB, which is a batch of data. What does that mean? I basically grab 16 images. Does that make sense, guys? In XB, there's 16 images. And in YB, there's 16 corresponding labels. So then I grabbed XB and I printed the shape. And what does that tell you? It tells you that it's a batch of 60 or a tensor of 16 by 3 by 32 by 32. You guys understand? What's the problem? The neural network wants 16 by 3072. Or if you only give it 1, then it wants 1 by 3072. Or if you change the batch size to 64, then it wants 64 by 3072. But you have 3 by 32 by 32. I think it's shut off. All right, so what's the solution to this? Huh? Reshape, right? So how do we need to then reshape this tensor, right? So what can we do? How do we do that? So I'm gonna stop it here. So let's see if you guys, well, this is starting up again, can think of a solution. So we need to go here. Okay, we're back. So we need to go here, right? And we need to reshape XB. Somehow, right? To now have 16 by, so what do we do? So there is, I don't know if I've introduced this function yet, but tensors, torch tensors have this function called view. Okay, that allow basically reshaping. So then let's see, I want to reshape it into 16 comma minus 1. Why am I doing that? Because I still want to keep 16 batches, right, which they were, but I want to take the last dimensions 32 by 32 by 3 and have it be flattened into one big vector of 3072. Does that make sense, guys? What I'm doing here? So let's go ahead and actually I shouldn't have removed xb.shape. So let's see the effect. So I'm going to do print. Let's see if it works. So xb.shape input, right? I'm going to repeat the exact same thing, but I'm just saying keep this -1. I don't know if I had introduced this before, but this -1 is, it's basically like saying to a, I want to reshape this tensor and I want you to keep this one dimension, the one that was 16. So we just put 16. But for the other dimension, we say -1. So what it's going to do is it's going to take the 32 by 32 by 3 and just produce the equivalent, but in one vector. Okay, and we can view that hopefully. So let's try that. So I need to do this. Then what do you guys think? Nice, right? Any questions? Yeah, please.
That's one batch.
That's one batch, exactly. So every batch, so in the data loader, there's still cubes, but before it goes into the model, which is the thing that matters, they're basically batches of flattened vectors. All right, great. So hopefully that makes sense. So yeah, so we're ready now. That was the hard part. One line of code, right? And then everything else should be exactly what we did before. So let's stop it here. One thing I also want to show you is that this model already can do inference. So what I mean by that is if I give it a vector, like an image, it will predict a class. It's just because it's not trained, it's going to predict badly. You guys see that? So it's not going to be able to predict the correct label. But let's just say test, or example label, right? So I'm going to predict. So I'm going to invoke the model. The problem I have is that I need an image, right? I need an image to give it. So I could take one of the images from the data set. That's a possibility. Actually, that's might be the simplest solution. So did we have one here somewhere? Here, this one, right? Data train. That's a torch tensor. So control copy. Yeah. All right. So let's think this one through. So I'm going to give it that, which is 3 by 32 by 32, right? This is really important. That goes into model, right? So in model, But model expects what? A flattened thing, right? So this will error out. So let me try it. See, it doesn't like it. And it says position must not torch size. So it's not, no, not, okay, sorry. This, I gave the shape of it. This is what I need to do. Now the error, yeah, matrix 1 and matrix 2 cannot be multiplied. You can see that there. Why? Because of the shape differences, right? So what do we need to do? We need to flatten this, right? So dot view -1. Do you see what I'm doing? So I'm trying to reshape it so that it goes into the model. Now it doesn't like it. It says expected to be in range of -1 to 0, but got 1 dimension out of range. Let's print this. I think this needs to be 1 by 32. These are what I'm doing this because these are going to be the errors that are going to make you cry. Okay, this is exactly what, you know, if you start changing things. Yeah, so okay. Dot, we need to dot shape. I need to know the shape of this. Okay, 30 by 72, and it's a torch tensor, but it doesn't like it. So my instinct is it doesn't like it because it wants it to be one, or let me put it another way. The next thing I would try is that if we gave it 16 by 3072, right? The tensors were 16 by 3072. It's reasonable to think that even though we're just giving it one, it wants 1 by 3072. But currently, we're just giving it 3072. Do you guys see what I'm saying? Do you get that? So I'm going to try to change this shape to say 1 comma 3072. So how can I do that? There's a function called squeeze and unsqueeze in Torch. All right, so I'm going to try to do that. I'm going to say, I'm also going to change this variable here. Okay, so run that, 3072. Now I want to take RC equal, there's a function called torch dot squeeze and unsqueeze. So there's squeeze and unsqueeze. And what that allows you to do is to add dimensions to things. Okay, so for instance here, I think I need to use unsqueeze. Yeah, unsqueeze. Okay. And I need to provide the RC thing, comma, and then I need to specify which dimension I want. So maybe 0, because I want to put it at the front. Do you guys see what I'm doing? And then I'm going to do rc.shape. Let's see if that helps. Ah, you see? So these functions that initially might seem like so abstract, like why do you need unsqueeze and squeeze? This is why you may need them, because 16 by 3072, so even if it's just 1, it may want it to be 1 by 3072. Does that make sense? Okay. So again, these are the things that if you start changing the code, they're the things that will trip you up, basically. Okay, so now the model, I believe, is expecting this. Otherwise, I'll need to try something else. So I already have RC in that shape, so maybe I can just plug that in there, like that. Okay, so let's try it. Like magic, right? Magically, it works now. Okay, and so now example label should have a label in it. So sample label. Oh yeah, that's right. So it doesn't have one label. Instead, it has a vector, because the output is a vector of size 10, correct? That's in the neural net here. So the neural net, remember, outputs vectors of size 10. Don't forget that, right? So that's what comes out of it. But the intuition of this is going to be that it's for the 10 classes. And it's basically what is called a probability distribution. So the one that has the highest probability, that's the one that you pick. That's your label. So in this case, if you guys look at all of these, which one would you select as the highest one? The third one, right? This one. So basically it would be which class? 2. There you go. That's the class. That's how it works. So that's how it ties to the architecture. Okay. So good. Now, so we've done that. Please, practice this. I would suggest practice it a lot of times because I do, these are common things that you have to play with that might cause problems. All right, so now what we need to do is we need to go to that train loop and just finish it, right? So I've converted it to where it's going to fit in the network. I know that because I do this view here, which is 16 minus 1, converts to batches of 16 by 30, 72. So now we are ready, basically, to do the rest, which is what? We give that tensor into the model. The model will predict, as I just showed you. And now we are going to give that the ypred to the loss function. So we invoke loss fn, which takes ypred, comma, yb. YB. Here's something really interesting. The vector that comes out of the model is a vector of size 10. But if you remember, the values in YB are just 3, 7, 5. They're not vectors. Yet we're comparing a vector of size 10 to a one integer number. In the past, you would have to take those labels and also convert them into a vector and do the comparison. But nowadays, it's become so easy that the cross entropy function, this one, just, it's kind of like they decided, you know what, this is how we should do it. So one, it can be the vector. The other one is just a label, and it just figures it out inside, okay? So you don't have to change it. Does that make sense? Any questions about that? Nope. All right, so, but remember, this is a vector of size 10, and this is just a number, so 7 or whatever. All right, once you have that loss, then comes the thing that does the heavy lifting here, the 3 functions that you always call zero grad, right? This zeroes out old values. Then you do loss dot backward. So this is, whenever you hear that deep learning has calculus, this is the calculus part. I'll cover this once we're done with this, we'll start getting into some of those ideas and how it works. But this is basically calculating the derivatives, calculating, how to update basically the weights, okay? And then the next step does the actual updating. So it's just going to be opt.step. And that's it. That's the whole thing. All right, then the last part here in this for loop is just to print the losses because we want to see those losses going down. So I'm going to say if epoch modulus and how many, I'm going to do, let's say, I'll probably need to do like 1,000 iteration epochs, but I'm only doing 100 currently. So let's just do 50 for now. And I just want to see how fast it runs, and I'll modify it based on that. So whenever epoch is a multiple of 50, it's going to print. Okay? So, oh, this should be epoch H. And then print epoch. loss equal loss. All right, so I think we're ready to run all of this and see what happens. So let's try it. Okay. So it's training, I think. There you go, it's running fast. So I'm obviously going to change the epochs here. It's taking about, that took what? To get that first one? Takes a bit, you see? And this is a GPU. See why you need a GPU? All right, so pretty slow, pretty slow. What are some suggestions that we can do here? One is the print of the losses. You can change that to every 10 so that you can see the data changing more often. What else can we do? Really, you can change that 200 to less. All right, so maybe 200 initially was not a good idea just because we were just trying to figure out how slow this was going to be. Okay, so let's see. Where are we? Still doing things. So what am I going to do? I'm going to stop it. Okay. Even though we're using a GPU, this can be pretty slow. So I'm going to try to just make this faster just by doing it like giving it 20. That's obviously probably not a good final model, but I'm just trying to like figure out how quickly it runs and that everything runs, rule out any bugs. What else can I do? I mean, I could change the batch size, but that just means more batches. So the learning rate could actually, no, it's not going to affect speed. It will affect in the end the results that we get, but not speed. So I think currently for speed, the only thing that helps is reducing the size of the number of weights that have to be updated. Hopefully it makes sense. When it was 200, we had 200 weights to update. Or not 200, but think of it in those terms, right? Whereas now 20 is fewer, so hopefully it'll run a little bit faster. Okay, I just want to see how quickly it runs. So let me try this.
You could, linear one.
Oh yeah, that's a pretty thing. Okay, thank you. All right, let's try this again. Still staying with 100 epochs just because I want to see how quickly this moves. Okay, there's that loss again. Oh. And it's really that image is the problem. That's really large in color. But this is why I choose CIFAR-10 is so that you get that experience of dealing with everything. And now you start to read, and hopefully now you're like, oh, maybe I should learn that NumPy. And maybe I should learn those matrix multiplications after all. You see what I'm saying? Because this is where it becomes real. All right, so I'm trying to think what else we can do. Well, another thing I'll do is, I guess, the epoch size, just so I can see something happening. I want to determine how long it takes, right? So I'm going to do 10, actually 5. And I'm only doing 100. So let's try this one more time. Okay. Training loop going once again. Now it's every 5, it should print the current loss. At least by doing this, you can figure out if this is going to run in 2 hours or 2 days or a week. Oh, there we go. See? So now I have an indicator. Okay, so this tells me it takes how much? Okay, from 10 to 15, it'll take 5 seconds. Do you think? So you can just do that. Usually I take out my phone and I start the timer between iterations, right? And then I'm like, oh, okay, it takes 20 seconds. And then I just calculate how many, and I know, all right, I'll be back in 3 hours. All right, so. Does this make sense, guys? These are very real things that you're going to have to do in CIFAR-10. Okay, now you know the GPU that you get only lasts 2 hours, right? So that's another thing. So you may need to save checkpoints. So at the end, just before 10 hours, you know, so when the GPU time runs out, you can just use the last checkpoint for the next 2 hours.
How do you do that?
Yeah, I haven't shown you the code, but it's easy. So you just save model and load model. But yeah, you're right. I have to provide. I did that for the data set, I believe. So I did something similar for the data set here. There, see torch.save and then torch.load. So it's something similar. So just like I'm printing here, losses every 5 epochs, maybe you would also save checkpoints. You see that? And you're going to end up with a lot of checkpoints, which is also a problem because you're going to fill up memory. So make sure you put it in the scratch space where you have 1 terabyte. Okay. And if the time that you are given for the GPU runs out, you can always just use that checkpoint for the next run of 2 hours. And this is standard practice. You know, it's not that the university actually has provided a really good resource for you guys. So that you just have to share. But okay, so let's look at the losses here. If you look at it, what can you observe about these losses?
They're not improving.
They're what?
Doesn't seem to be improving.
They don't seem to be improving. So 221, 215, yeah, 214, 191 is kind of like fluctuating. See, this is a difficult problem, right? But I promise you, you can get good results with this. It's just going to take work. First of all, we're using a multi-layer perceptron, right? So we're going to change that to a deep neural network. If you're using a deep neural network, though, what does that mean? It's going to take longer, more neurons, more layers. So these are the trade-offs. And this is nothing in comparison to something like ChatGPT or those are incomprehensible how big they are. All right, so it's going to finish at 100, I believe. Right? Yeah, it finished. There you go. So the code runs. That's basically how it works. So I'm just going to go with this model. Now, is this model, are the weights of it random or are they more trained? They're more trained, right? So it may not be a perfect model, but it's no longer random weights. You know, the training function has looked at the training data and has tried to create an architecture to predict. So what I'm going to do now is I'm going to use this model to predict basic. And I'm going to calculate performance. Okay, so I ran the core functions. Now all I need is And this code I can just copy from the iris example. So if you remember, you just go to the machine learning foundations folder, go to neural nets, PyTorch. And this is where the iris example is that we did in class earlier. And this is where I will load this one, CIFAR-10. But I just need to add two, I will need actually these. We've covered these before, if you remember. These are the performance metrics. Okay, so let's just add a new cell here. Okay. Remember, the model's already trained, and it's in the where's the model that's already trained? How do you get it? Where is it? The model you just trained, where is it? If you want to now do inference with it, it's right here. You see that? You could save this as a checkpoint. You could also deploy this with Onyx. Load it on your website like we did with the KNN averaging. You know, all of that. But what I want to do now for the challenge is evaluate that model. So I'm going to copy just two cells, which should be, right? This one, this function should be familiar to you guys. Performance metrics. Okay. And also, and I've already explained this, but I'll explain it again. This code segment. All right, so important, really important, because I can't really control this part. Always run it, when you're dealing with a test set, always run it with this statement. This statement says, with torch, no grad. What that means is the model is going to look at the test set. But if you don't write this and the model looks at the test set, then it's going to update the weights also based on that. And that's cheating. Okay. And there's no way for me to control that. So always run this code and nothing else. Okay. So that way you're ensuring that the model, yes, it looks at the test set, because you might do this multiple times. Like you try something and you keep trying it. And then eventually it's like, oh, wow, it does really well, but it's seen the test set. Okay. And that's like giving it some information that it didn't have before. I don't know if it's going to be a significant improvement, but it could be. Right. So that's a standard practice you do this. So with torch, no grad, right? You just do that. That means the weights will not be updated. We created test data loader, I think, already. Let's just confirm that the name is testDL. Okay. And we are grabbing all 10,000 at once. We're not going to grab in batches. So then basically XReal and YReal. XReal contains 10,000 images and YReal contains 10,000 labels. Everyone with me? Very similar to the training part. Questions there? We need to give XReal to the model for it to predict. YPred then, notice, because it's a vector of 10, it's going to do this torch max. What does torch max do? It returns the index of the highest value in that vector. You guys already did that manually when we did this, right? Somebody said, this is the highest. So what you did is you use torch.max in your brain. Torch max does the same. It looks at the highest value, but it doesn't return 0.114. It returns the index where that value is, effectively giving you the class. Got it? All right, so we get the label, vals and indices here. Actually, it returns vals and indices, but we only need indices. So indices, I just did this too because I like to use these names. So I use preds, and then I provide to print metrics preds and compare it to YReal. Got it? Is this gonna work? If I do this, doesn't work. Why? The shape. This is 10,000 by 3 by 32 by 32, but the neural network needs it to be 10,000 by 3072, right? So what do you need to do? We already have the code for that. Just go to the train function, and here it is. Right? So we can go over here. Oh, where is it? Here. See, it's a very neat place to do this. Now we need to change this, right? So we know this is 1,000, but another easy way of getting this is what I was doing here. Batch size. So then you just do what? X real, right? That way you don't have to, like, you should never hard code numbers into your programs. You're just creating a serious problem later. So here, if I grab X real, shape 0, that should give me 10,000. So then batch size, you can just write batch size here. But it's effectively just hard coding 10,000. Does that make sense, guys? All right. Now the -1, you already know, right? It's going to take that 3 by 32 by 32, spaghettified into 3072. All right, so now this should work. XB is not. Oh, yeah. So X real. That's X real, right? X real. Is this correct? Yeah. Right, so I need to grab X real, reshape it, and then go, yep. All right, and it worked. Look at that nice confusion matrix. F1 measures 0.13. I'm probably in worst place, right? At this point in the competition. Whoever gets the highest here from 0 to 1 wins. And you have a long journey from 0.13. Okay, that's it. That's the whole challenge. So this is the basic code that I was going to give you. On I know we're almost out of time. On Thursday, I will do the deep learning algorithm. But as you can see, I'm having a hard time with this because it takes too long to train. I'm pretty sure if I did a multi-layer perceptron with like 200 neurons, it'll get a little bit better. I'm going to start throwing things like batch normalization, other activation functions, etc. And hopefully it'll improve. As you can see, the batch size, we're using the thing that has 10,000 samples. That's not the problem. The slowdown is during the training and the weights updates, right? So that takes a long time. This confusion matrix, all the values should be on the diagonal. So again, your goal for this challenge is to arrive at the best set of metrics for this, using exactly as we did, train set, test set. So your work is somewhere in here, 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 somewhere in here. And then pretty much the data loaders you don't have to change. Except for the batch size. You might try bigger batch sizes. And so got it, guys? All right, so I will post this code, given that it's complete code now, on the same place on the GitHub, which is here. So you'll see this in a little bit. And then on Thursday, we'll just keep trying, giving you ideas. Just keep in mind, we may not be able to run everything because the deeper and bigger it is, the slower, and we'll never see the results in 20 minutes or so. Got it? All right, guys, so start playing with this, load your data, and I'll see you on Thursday.
Or in ensembles cheating
On
or PyTorch transformers.
I did say that you can use the Torch hub. So if you're gonna use something like transfer learning, it's gotta come from Torch itself. Like Torch has this thing called torch.hub, and then there's a few models in there that are pre-trained. You can use that. If you notice, that's not in the rules I said, that's fine.
Yeah, I was like, oh, it's not in there, so we can't do it, so.
Yeah, so you can. If it's PyTorch.hub, you can.
And we can do ensemble. And
If it's in Torch.
Yeah.
Hub, yes. Run it by me first, just to make sure it's, not giving you an unfair advantage, but. Because what part of this is kind of from scratch to figure out how to make this better, you know what I mean? But, yeah. All right, great.
Updates.